Meteorites are fascinating remnants of the universe that allow us to peer into the early days of our solar system and even the formation of the universe itself. These space rocks, which originate from comets, asteroids, and sometimes even the Moon or Mars, travel through space and eventually fall to Earth, offering scientists a unique opportunity to study their composition. Meteorites provide valuable information about the materials that existed in the solar nebula, the cloud of gas and dust from which our solar system formed, giving us insight into the building blocks of planets, moons, and even life. So, what exactly are meteorites made of? To understand their composition, we need to examine the different types of meteorites and their primary components. Meteorites can be broadly classified into three main types: stony meteorites, iron meteorites, and stony iron meteorites. Each of these types has a distinct composition, offering clues about the processes that occurred during the formation of the solar system. Let's start with stony meteorites, which make up about 94% of all meteorites. These meteorites are primarily composed of silicate minerals, such as olivine, pyroxene, and feldspar. These minerals contain silicon and oxygen, which are two of the most abundant elements in the Earth's crust. Stony meteorites are further divided into two groups: chondrites and achondrites. Chondrites are the most primitive type, and they contain small, spherical particles known as chondrules. These chondrules are tiny droplets of molten rock that were once part of the early solar system, before the planets had fully formed. The presence of chondrules in these meteorites is a crucial piece of evidence that helps scientists study the conditions and processes that occurred in the early solar nebula. Achondrites, on the other hand, are stony meteorites that do not contain chondrules. These meteorites have undergone some form of processing, such as differentiation, where the materials inside the meteorite melted and separated into layers, much like how the Earth itself formed distinct layers. Achondrites are often thought to originate from planets or large asteroids that underwent volcanic activity, such as Mars or the Moon. The study of these meteorites provides important information about the geological processes that shaped rocky planets. Next, we have iron meteorites, which are primarily composed of iron and nickel, two metals that are dense and found in large quantities in the core of planets and asteroids. These meteorites typically contain about 90% iron and 10% nickel, and their structure often displays a distinctive Widman-Staten pattern, which forms when the meteorite is cooled slowly over millions of years. This pattern is made up of interlocking crystals of iron-nickel alloys. Iron meteorites are believed to originate from the cores of differentiated asteroids, which, like planets, underwent melting and layering. The study of these meteorites helps us understand the formation of planetary cores and the processes that lead to the differentiation of large bodies in the solar system. Finally, stony iron meteorites, as the name suggests, contain a mix of both silicate minerals and metal. These meteorites are relatively rare, but they provide a fascinating look at the transition between the rocky material of the asteroid mantle and the metallic material of the asteroid core. The most well-known stony iron meteorites are pallasites, which contain large olivine crystals embedded in a metal matrix of iron-nickel alloys. The study of pallasites provides insight into the conditions under which planetesimal small building blocks of planets formed and differentiated. So, what can the composition of meteorites tell us about the solar system's formation? The different types of meteorites are a snapshot of the various processes that occurred during the early days of our solar system. Stony meteorites, with their chondrules, represent the first solid materials that formed as the solar nebula cooled, while iron meteorites tell the story of planetary differentiation and core formation. Stony iron meteorites, on the other hand, offer a glimpse into the boundary between rocky mantles and metallic cores, helping scientists understand the early stages of planetary formation. Meteorites also provide evidence about the chemical building blocks necessary for life. Many meteorites, especially carbonaceous chondrites, contain organic compounds, such as amino acids, which are the basic units of proteins. This has led scientists to hypothesize that some of the key ingredients for life on Earth may have been delivered to our planet by meteorites. The presence of water and organic material in these meteorites supports the idea that extraterrestrial bodies may have played a role in the origin of life on Earth, an idea known as panspermia. One important aspect of studying meteorites is how they help astronomers and planetary scientists understand the history of the solar system. By analyzing the isotopes in meteorites, scientists can determine their age and gain insight into when the various materials in the solar system began to condense and form solid bodies. This process, known as radiometric dating, allows researchers to estimate that meteorites, particularly chondrites, are around 4.6 billion years old, approximately the same age as the Earth and the Sun, which gives us a direct link to the very beginning of our solar system. In conclusion, meteorites are not only a fascinating collection of materials from space but also invaluable scientific time capsules. By studying their composition, scientists are able to unlock the secrets of the solar system's formation, understand planetary differentiation, and explore the chemical building blocks of life. Whether they are stony iron, meteorites offer us a tangible link to the past and a deeper understanding of the processes that shaped our solar system and possibly life itself. For students of astronomy, understanding meteorites is key to grasping the broader picture of planetary formation and the conditions that led to the development of the planets and life on Earth.